Hello guys, in this video we are going to see some examples of basis, dimensions and some spaces. Okay, so in the previous video we saw what was the basis. So if V is a vector space, oh that's a typo over here, this is space. So if V is a vector space and B is a set of some vectors which have linearly independent vectors. So all these V1 to Vn are linearly independent vectors and the span of B. So we know what is a span. So the span is all linear combination of these vectors, right? So if the span of B is equal to V, which is the vector space, so these vectors span the entire vector space, then we can say that B is the basis for V. Okay, so that is what is basis. Then we go forward to dimension. What is a dimension? So the number of vectors in B, the basis set, is the dimension. So if there are n vectors, then it is n dimension. You can also see it as the number of free variables. We'll see in the example what do we mean by free variables. Right, so the first example, let's talk about symmetric matrices. So if say your vector space is Rn cross n, where you have square matrices in your vector space, the vector looks something like this, and your field is real, suppose. And then what is a symmetric matrix? So if A is a matrix, then A should be equal to A transpose for symmetric matrix. So all symmetric matrices follow this criteria. Now let us consider a special case for n is equal to 3. So we are now in R 3 cross 3. So a symmetric matrix will look something like this. So you see that if this is 1 2, then this is also 1 2. So these two are same. 1 3 1 3, these two are same, and these two are same, right? 2 3 2 3. Diagonals may be anything, right? So this is how a symmetric matrix looks like. Now the first question that one may ask is it a subspace? So if you have one symmetric matrix, you have another symmetric matrix. If I add both of them, will it give me a symmetric matrix? Further, if you multiply it with a scalar A, if you multiply the first matrix with a scalar A and the second matrix with a scalar B, and then you add both of them, that is, if you have a linear combination of two symmetric matrix, will you get a symmetric matrix? Right, so that is the questions that one may ask when it wants to know if it is a subspace or not, right? So let's look at that. So is a set of symmetric matrix a subspace or not? So let A and B be symmetric matrices. Now we are in the general case in R n cross n. It can be any n cross n symmetric matrix. So let us define a C, which is nothing but A. A is a scalar that comes from a field, which is R over here. So the field is real now. So A is this, and this small b is also coming from the field. It is a scalar. Okay, so this is the linear combination. Now is C also symmetric is our question, right? So take the transpose, let us see. So let us take C transpose. If you take C transpose, so A is a scalar, so that will not matter. So it just come out of it. And A is this capital A is a matrix, so you'll get A transpose plus B again is a scalar and you'll get capital B transpose, right? Now we know that A and B are symmetric. So A transpose can be equated to A and B transpose can be equated to B, right? So you get C transpose equal to this, both are same, and B transpose and B are same, right? So which is nothing but C, right? This was what we started with. So we can see that C transpose equals to C. So that proves that C is a symmetric matrix because C transpose also equal to C. And yes, it is a subspace. So a set of all symmetric matrices are a subspace. Okay. The other question is, can we find out the basis and the dimensions as well? So what will be the basis of this subspace, this symmetric matrix subspace, and what will be the dimension? Okay, quite simple. So say, let us take a special case for n is equal to 3. So the vector looks like this. Suppose the field is real. So a symmetric matrix would look something like this, right? Now, if you see carefully over here, this A11 is a free variable. So I mean, I can put any number for A11. I can put 1 or 2 or something, right? Now A12 is another free variable. If suppose A12 is 2, automatically this will also become 2, right? Because these two are the same. So if this is 2, this will also be 2, right? So these two are like a pair. And same case for A13 and A23. So if A13 is suppose 5, right? So this A13 will also become 5, right? And for A23, say suppose this is 0, then this will also become 0. And A22, A33 can be any number. So this can be say 7 and this can be say 3, right? They can be any numbers. So by this you can actually get an idea of the basis. So the first basis can be around A11. So just having A11. So something like this. So I am just putting a 1 at A11 and all others are 0. So it is this basis is just focused on A11. That's all. Right. So this basis is just focused on A11. Now if you look at this is focused on A12. So now because if you want to change A12, you'll also have to change this one. So there are two of these, right? Like over here, right? And then for A13 you have this. For the others, so for A23 you have this. For A33 you have this, and for A22 you have this. Now if you want to make this matrix, this one over here, what you'll have to do is just multiply these with appropriate scalars. So you want A11 as 1, so you don't multiply, so just 1 over here. If you want over A12 as 2, so you just multiply by 2 over here and add both of these, right? You want A13 as 5, just multiply this by 5 and add. So similarly, you understand the logic, right? Just multiply this by 0, multiply this by 3, and multiply this by 7. So like this, by the linear combination of any of these 6 matrix, you will get any symmetric matrix of the order 3 cross 3, right? So that was about 3 cross 3. And by this you can also judge the dimension. The dimension is 6, right? Because there are 6 bases in the basis vector. But now how to generalize this? So you can actually generalize the dimension. For bases it is quite simple, right? If you have 4, say 4 cross 4, so accordingly you will have different bases. So it will be 4 cross 4 matrix, and then you can have one over here, and then there will be more, right? You get the logic, right? So about the dimension, so say for an n cross n, what will be the dimension? So the dimension will change, right? So that is simple. I mean, so if you see over here, you got 6. How did you get that? So this is nothing but the number of free variables over here. So if you see A11, A12, A13, A22, A23, and A33 are the free variables. Okay. So these are the variables that you have to decide. So that makes your dimension. So over here in the first row, you have 3 free variables. So that is 1, 2, and 3. And the second row you have 2 free variables, A22 and 23, because this becomes fixed. And in the third row you just have 1, right? Because it is just A13. And the multiplication 3 into 2 into 1 will give you 6, right? So this is how we got 6 over here, the dimension for 3 cross 3 symmetric matrix. Now, if you have an n cross n symmetric matrix, what will happen is you will have n over here because there will be n columns, right? For the second column, you will have n minus 1. So this is the general case, okay? If suppose you have an n cross n symmetric matrix. And like this, it will go on, right, till you reach 1. Right. I'm sorry. I said multiplication, right? It is not the multiplication. It is addition, right? Because you are just adding 1, 2, 3, 4, 5, 6, right? So it is 3 plus 2 plus 1. That's it, right. This is not 4. Okay, this is plus. So it is the addition of these. So if you see over here, it is n plus 1 up till 1, right? So this is nothing but the sum of natural numbers. So we have a formula for that, and the formula is n into n plus 1 plus 1, and that's a 1, okay, by 2. So that is our formula for the dimension of n cross n symmetric matrix, right? This is a 1, okay. Okay, quite simple. Now similarly, you can see for a skew-symmetric matrix. So for a skew-symmetric matrix, A is equal to minus A transpose, right? And then for n is equal to 3, this is how your A will look like. So notice you have zeros at the diagonals, because for this minus to occur, you should have some number whose negative is the same as the number, which is only 0. So only 0 is equal to minus 0, right? So you can have only uh, zeros at the diagonals. Now, is it a subspace? Again, going through the same logic, say A and B are skew symmetric. So C, a new matrix, will be equal to small a into capital A plus B into capital B, where A and B are scalars, right? And these two are skew symmetric. Now, is C skew symmetric? Well, take the transpose, and if you see over here, A transpose will become minus A, B transpose will become minus B. You take the minus common outside, what will happen is this is what will happen, and then this is nothing but C, so you get minus C. Simple, right? So over here you can see C transpose is minus C, hence C is also skew symmetric, right? Is it yes, it is a subspace, right? Because the linear combination of two skew symmetric matrix is giving you a skew symmetric matrix. It is a subspace. What is the dimension and basis? So over here you see there are zeros on the diagonal, so then these are not free now, only these variables are free. So by this you can understand the dimension is 3, because only 3 free variables are there, and accordingly you can also figure out the basis. It is simple, because a12 is something that you have to fix, a13 and a23, that's all. So you get only 3. So now for this what happens is you get 2 over here, only 2 free variables, and you have only 1 free variable over here, and you have no free variable for the last row, right? No free variable, 0. So you add all of these, so you get dimension is equal to 3, right? For the n case, if you see 2 is nothing but so there'll be a 0 for an n cross n as well, so all diagonals are 0. So this will be nothing but n minus 1, right? So this is n minus 1, this is n minus 2, n minus 2, and like this you go on up till you reach 0, right? So for this what will happen is your formula will, so for the skew symmetry for the symmetric case, if you remember, uh, oh sorry, yeah, so over here it was n into n plus 1 by 2. So if you just replace n by n minus 1, so this n will become n minus 1, and here you'll have n minus 1 plus 1, that will become n, right? I'll again write it for you, right? So over here you have n minus 1, so it is like n minus 1, and then if you see the formula, because this is again the sum, right? So you get over here n minus 1 plus 1, because of that formula. So if you want sum of n numbers, right, upon 2, so this is nothing but this both will cancel, n into n minus 1 by 2, right? So the dimension formula for an n cross n symmetric skew symmetric matrix becomes n into n minus 1 by 2. So if you see here, it is 3, because for 3 dimension it is 3 into 3 minus 1, that is 2 by 2. So that is 3 into 2, 6 by 2, 3. Okay, quite simple, right? So that is how you can find the dimension. So please remember, for any other general case, you just have to see how many free variables are there, and that is your dimension. Okay, so that is a quick trick to find out the dimension. And the bases are these, and these can also be called as standard bases, because these are the most simple bases, right? So yes, so these were some of the examples of basis, dimension, and subspaces. So that's all for this video. I hope you got to learn something, and thank you so much for watching. Thank you.